Hello guys, before we proceed with the concepts on torsion, I'd like to present first a basic example of how flexural buckling or global buckling are carried out in terms of the solution to problems. So here in our example, we are simply asked to determine the compressive strength of your WT12 by 81 A992 steel, and the properties of this section is actually given, but in case these are not sufficient, we can refer to the AISC manual to get additional properties. Okay, so the effective length are also given in terms of KL parameter, wherein the XYZ values for effective length are shown. So the XYZ subscript simply refers to the right-handed coordinate system in terms of this orientation. Okay, wherein your z-axis is actually directed along the longitudinal axis of the member, passing on the centroidal axis of the section. Okay, so if we have here a section, okay, so this section may actually be represented by a shape. Let's say I have here a wide flange section. So more or less the orientation of X, Y, and Z is originated at the centroidal axis of the member. So this is your column. So this is the length involved on such a member is actually constant. So L here is constant, but since the effective length factor K, X, Ky, and Kz are not equal, no? So the values of K, L in each direction may not be equal also. Okay? So for the Z direction, we have to bear in mind that this is the torsional direction. Y is bending about Y, about Y-axis, and X is actually bending about the Z-axis. Okay, so bending or simply buckling. So I may refer to the when I say bending, I'm referring to the buckling. So in this example, you will notice that the buckling is directly assumed to occur critically at the x-axis. But if in case you don't know the critical buckling axis, you can compute both. Okay. Of course, torsion is not yet included in this example because we're not yet through with torsion. So we might as well look into the two values first and compute for both kxl over rx and compare it with kyl over ry. Okay, so whichever is greater, you may use the more critical. Okay, so x-axis is the more critical axis of buckling, since your kxl over rx, which is 87.43, is greater than this value here. Okay, so you may compute the kyl over ry. So the value here will be less than 87.43. So in case this is greater than that, you have to take note that your flexural buckling of the y-axis will govern, hence the more critical axis of buckling. So for the next step, we ought to determine the limit for inelastic and elastic buckling. So this formula here gives you the limit or the boundary. The curve for the column strength is actually half bell curve. Okay, so it looks like a bell curve like this, where in the point in between serves as your limit for the value of your KL over R. Okay, so this KL over R is referred to in other books referred to your CC value. Okay, wherein your CC is simply equivalent to this value here, or simply 2 pi squared E over Fy. Okay, which is equivalent more or less to 4.71 square root of E over Fy. So actually the value used here is not 2, but rather it's 1.5 squared. Okay, it's not 2 but 1.5 squared. And this has something to do with your lambda sub c squared as the basis for your LRFT limit. Okay, so upon computing this limit and you found out to be 113, you just compare the actual KL over R with that of the limit, and since the limit is bigger than the actual, then your behavior will be an inelastic buckling behavior, which belongs to this side here. Okay, so this is your value 87.4. Okay, so it is an inelastic buckling mode of failure, so that your FCR is simply computed on the basis of this formula. Of course, we need to find first the Euler buckling load Fe given by the formula here, and which happens to be 37.44 KSI. And upon substituting, FCR becomes 28.59 KSI. So this is what you refer to as your critical buckling stress, or yes. Stress or strength. Okay, and if you want to find the nominal actual load capacity of you simply multiply it by Ag, given to be 23.9, and this is what you call now the nominal actual load capacity of of your column. Okay, so that solves the problem for simple flexural buckling analysis, or you call this also a global buckling analysis uh, example. So thank you very much, and I'll see you on the next video.